Hi, in this video, we'll continue our problem solving course. Today, I'm going to look at 5 problems from RMOs. The first problem is RMO 2014, and this is an inequality problem. Let X and Y be positive real numbers. We have to prove that 4x power 4 plus 4y cube plus 5x squared plus y plus 1 is greater than equal to 12xy. So this is an example of how powerful ANGM can be, ANGM inequality. And we'll see how a correct grouping here will give us the answer very easily. So here, because x and y are positive real numbers, we can apply ANGM to any of these terms. We will say 4x power 4 plus 1 will be greater than equal to twice of root of 4x power 4 times 1, which is equal to 4x squared. This is applying ANGM on these two terms. Then we can also say 4y cube plus y will be greater than equal to twice of root of 4y cube times y, which is again equal to 4y squared. So this and this have been grouped. This and this have been grouped. So basically you have 4x power 4 plus 4y cube plus 5x squared plus y plus 1. By 2 times applying ANGM, we can say that it is greater than equal to 4x squared plus 5x squared plus 4y squared, which is equal to 9x squared plus 4y squared. And then finally apply ANGM once more to this two terms. This is greater than equal to twice of root over 9x squared into 4y squared, which is 6xy. So this is 12xy. So we have proved that this is greater than 12xy. So a very simple problem, but if you don't get the correct grouping, it will be difficult to do. You are applying ANGM 3 times. That's how you solve this problem. Let's look at another problem. 107. This is also RMO 2013 this time. And here we have given that A, B, C, D, E are greater than 1. We have to prove A squared by E minus C minus 1 plus B squared by D minus 1 plus C squared by E minus 1 and so on. D squared by A minus 1 and E squared by B minus 1 is greater than equal to 20. Okay. So another inequality problem, again we'll be using ANGM, but before that, we have to see how to get something like A square and A minus 1 or B minus 1 and inequality based on that. So what we can say is A minus 2 whole square is clearly greater than equal to 0. So A square minus 4A plus 4 is greater than equal to 0. So A square is greater than equal to 4A minus 4. So A square is greater than equal to 4 times A minus 1. So we get A square by A minus 1 is greater than equal to 4. And notice that there are 5 terms like this. But the problem is we cannot directly do that because we don't have A square by A minus 1. We have A square by C minus 1, right? So we don't know anything about this right now. But we know that similar terms, we can say an inequality like this, right? Okay, so let's, because here notice that A minus 1 is positive. That's why we were able to divide and not change the sign of the inequality, right? So let's apply ANGM to these 5 terms. We can say that this expression LHS will be greater than equal to 5 times 5th root of A square by C minus 1 times B square by D minus 1 times C square by E minus 1 times D square by A minus 1 times E squared by B minus 1. And now, since all of these are factors now and they are multiplied, we can rearrange it and write it as A square by A minus 1, B square by B minus 1, C square by c minus 1 d squared by d minus 1 and e squared by e minus 1. And all of these are greater than, this is greater than equal to 4 into 4 into 4 into 4 into 4. So 4 power 5. And because there is a fifth root here, we get that LHS is greater than equal to 5 into 4, which is 20. So we have to apply ANGM on all these 5 terms, and you have to notice this fact and then rearrange this here in order to get the proof. So 2 pretty easy inequality problems which are solved by ANGM inequality. Let's move on. This is problem 108, which is from RMO 2013. This says a polynomial is called a Fermat polynomial if it can be written as the sum of squares of two integer polynomials. Suppose that f of x is a Fermat polynomial and f of 0 is equal to 1000. We have to prove that f of x plus 2x is not a Fermat polynomial. Okay. So a definition has been given to you. A Fermat polynomial is a polynomial which can be written as the sum of squares of two different polynomials. And those two polynomials must be integer polynomials. By integer polynomials, we mean that their coefficients are integers. Now, f of x is a Fermat polynomial and f of 0 is 1000. So we have f of x can be written as p of x squared plus q of x squared, where p of x and q of x are integer polynomials. We also know that f of 0 is 1000, which means 4 divides f of 0, right? F of 0 will be the constant term of the polynomial, right? So what will be f of 0 value? F of 0 is equal to g of 0 squared plus h of 0 squared. So we know that 4 divides g of 0 square and h of 0 square, the sum of them, right? Now, if you look at quadratic residues modulo 4, we know that squares of integers are always either 1 mod 4 or 0 mod 4. Now think about it. If the squares of integers are always 1 mod 4 or 0 mod 4, if it was 1 mod 4, if the square of g of 0 was 1 mod 4, if this was 1 mod 4 and this was 1 mod 4, the overall would be 2 mod 4 and then 4 will not divide that, right? So what this means is that g of 0 square must be basically congruent to 0 mod 4. So it is divisible by 4. Then only you can add g of 0 square, and similarly h of 0 square must also be congruent to 0 mod 4. G of 0 and h of 0 are integers. The squares of integers can either be this modulo 1 or 0 mod 4. If any one of them was 1 mod 4, you would not get the overall sum to be divisible by 4. But we already have that. 4 divides 1000 and 4 divides f of 0. So that means that g of 0 square and h of 0 square must be 0 mod 4, which implies that g of 0 and h of 0 must be even. and h of 0 must be even. Then only the square will be divisible by 4. There is no other way. So g of 0 and h of 0 are 0 mod 2. That is what we have figured out so far, right? So from the data here, f of 0 is 1000. We have figured out that the constant terms of the gx and the hx polynomial are divisible by 2. H of 0 are congruent to 0 mod 2. Okay. Now let's focus our attention on the, okay, first we'll say, I am writing G and H here. I made a mistake. I should have written P and Q, or I will just correct this. This is G of X square plus H of X square, where Gx and Hx are integer polynomials, right? Now, if you think of the Gx polynomial and the Hx polynomial, let's write the coefficients of this. It will be Gn minus 1 till G1 and G0. And Hx coefficients are Hn minus 1 till H1 and H0. These are the coefficients of all the terms of the G and the H polynomial. These are all integers because it was integer polynomial. Now think about it. What is G of X square? When you square this, you will get many terms which will have X square term. And then you will get many terms which have X coefficient, right? Actually, not many terms. There will only be a few terms with X coefficient. The term with X coefficient in this would be 2g1 g0 x, right? Think about how you would square g of x and get the x term from there. The only way you can get x term is multiply g1x with, okay, I will just show this in the next screen. Let's say g of x was gn x bar n plus gn minus 1 x bar n minus 1 till g1x plus g0. So g of x whole square will be the square of this. The square of this will have many higher order terms. When you square each of the terms, then there will be all the terms which will be multiplied 2 at a time, right? So notice that if you have g2x square here, you will never get an x term from any of the two groupings, right? The only way you can get an x term is 2g1 g0 x, right? This is the only term that gives x power 1. So therefore, coefficient of x in f of x is, since f of x was g of x square plus h of x square, it would be, coefficient of x would be 2g1 g0 plus 2h1 h0, right? This is the coefficient of x in f of x. Now, if you think about it, we have already decided that 2 divides g0 and 2 divides h0 because the g of 0 and h of 0 were said to be even. So that means 4 divides 2g1 g0 plus 2h1 h0 because 2 is a factor of this and 2 is a factor of this. So both the terms are divisible by 4. So that means 4 divides coefficient of x in f of x. Now, as long as f of x is a Fermat polynomial, 4 should divide the coefficient of x in f of x. But now, what do we have? The new polynomial is f of x plus 2 of x. So the coefficient of x here is 2g1 g0 plus 2h1 h0 plus 2, which is congruent to 2 mod 4. And therefore, it is not divisible by 4. Not divisible by 4. And therefore, this new polynomial f of x plus 2x cannot be a Fermat polynomial. For a Fermat polynomial, we have established that 4 will divide the coefficient of x. And now here in this new polynomial, you are getting it as 2 mod 4. So therefore, it's a contradiction and we cannot have a, we have proved that f of x plus 2 of x plus 2x cannot be a Fermat polynomial. Okay, let's look at the next problem. This is problem 109, and this is a number theory problem from RMO 2013. So this problem says find all 4 tuples A, B, C, D of natural numbers with A less than equal to B less than equal to C and A factorial plus B factorial plus C factorial is equal to 3 power D. Okay, so we'll go about this in steps. First, let's think about the value of A. So first claim that I will make is if A is greater than 1, then A could be 2, right? And if A is 2, then B will be bigger than 2 and C will be bigger than 2. So then what you will get is left-hand side, which is A factorial plus B factorial plus C factorial, will definitely be greater than 2 factorial plus, it will be 2 factorial and higher factorials, right? But all of these higher factorials are even. So LHS will be even, but RHS is odd. RHS is odd, why? Because 3 power D has no factor of 2, right? So therefore, A greater than 1 is not possible, right? So therefore, A must be 1. So we have concluded about the value of A. Now let's look at B. If B is greater than 2, if B is greater than 2, what you will get is B factorial plus C factorial is divisible by 3. Why is it divisible by 3? Because if B is greater than 2, the smallest number it can be is 3. 3 factorial is divisible by 3 and any higher factorial will also be divisible by 3. But A factorial plus B factorial plus C factorial, which is equal to 1 plus B factorial plus C factorial, will not be divisible by 3. Will not be divisible by 3. I hope you understand why this is not going to happen, because this part is divisible by 3, but 1 plus that would make it 1 mod 3. So it is not divisible by 3. However, RHS is divisible by 3. RHS is divisible by 3, which shows us that B cannot be greater than 2. So the possible values of B are 1 or 2. We already know A is 1, and now we have two cases for B. B could be 1 or 2. Now let's work on these two cases. So case 1 that we will take is A is 1 and B is 1, right? In that case, the equality becomes 1 plus 1 plus C factorial is 3 power D. And you have basically 2 plus C factorial is 3 power D, right? You can easily see that C is equal to 1 and D is equal to 1 is a solution, right? So one solution is obvious. 1, 1, 1, 1 is a solution that satisfies. If C is equal to 2, you don't get any solution because you get 4 is equal to 3 power D, which is not possible, right? If C is greater than 2, what will happen is the LHS will be even, because any higher factorial, 3 factorial and all is even, and 1 plus 1 is 2. So LHS will be even, but RHS is odd. So C greater than 2 is not possible. C is equal to 2 also doesn't work. So the only solution in case 1 is 1, 1, 1, 1, right? And now we go to case 2, where A is 1 and B is 2, right? And in this case, the equation for us becomes 1 plus 2 factorial plus C factorial is 3 power D, which is C factorial is equal to 3 power D minus 3, which can be written as 3 into 3 power D minus 1, which shows us that 3 divides C factorial. However, 3 square does not divide C factorial, right? 3 is clearly a factor of C factorial, but 3 square is not a factor because this is not divisible by 3. So we know that 3 divides C factorial and 9 does not divide C factorial, right? So then let's try to make a claim for what could be the value of C. So we know that C should be between 3 to 6, because if C was 6, then 6 factorial, actually 9 divides 6 factorial. You should realize that, because 9, there will be a 3 there and there will be a 6 there, which will give us 9 divides 6 factorial. So C cannot be 6, right? C must be lesser than 6. So we have 3 cases for C. C could be 3, 4, and 5. And now it's a simple matter of checking what happens in all of these 3 cases. You can now check that if C is equal to 3, then you get 1 plus 2 plus 3 factorial, which is 6, so 9. So D is equal to 2 is the solution. And if C is equal to 4, you get 4 factorial is 24 plus 2, 26 plus 1, 27. So then D is equal to 3. But if C is equal to 5, you get 5 factorial 123. 123, there is no solution, because 123 is not a power of 3, right? So the two solutions that we get here are A is 1, B is 2, C is 3, D is 2. And the next solution is A is 1, B is 2, C is 4, and D is 3. And these are the only 3 solutions possible for this equation. So this is the solution. We worked through the cases. We realized what conditions. We basically checked the parity of both sides of our equality, and from even and odd we can figure out a lot of things about A and B, and then we do some case work, right? Okay, let's look at another problem. This is problem 110, and this is a geometry problem from RMO 2013. So it says, let ABC be an acute angled triangle. Acute angled triangle. The circle tau with BC as diameter, intersects AB and AC again at P and Q, respectively. We have to determine angle BAC given that the orthocenter of triangle APQ lies on tau. Okay, let's draw the figure first, and we'll try to understand what is going on. This is ABC, acute angle triangle, and we have to draw a circle with BC as diameter. Let's draw a rough circle. The figure is not accurate, but we'll just work with it. This is a circle with BC as diameter, right? And what we can say here is this circle cuts AB here at P and this here at Q. And we'll join this. And what we can say is APQ's orthocenter, triangle APQ's orthocenter lies on the circle. So somewhere here is the orthocenter of APQ, which is H. So notice this figure. This is the figure. We are magnifying this portion of the figure. And let's find the orthocenter. Orthocenter will come by altitudes like this. This is my H. This is my H, and the circle passes through this. The circle will basically pass through H also and Q also. This is the situation. Okay. Fine. Now, let's first try to figure out what is the angle PHQ, angle PHQ. So anytime you have a orthocenter, you can always find all the angles, because if I join HQ right now, you can find all of these angles in an orthocenter sort of a figure, a pedal triangle sort of a situation. So let's find PHQ. What we will say is this angle here, QPH, this angle is equal to 90 minus Q, because this is 90 and this is Q, right? And similarly, angle HQP, this is orthocenter, so that will be 90 minus P, right? Angle HQP is 90 minus P, angle HPQ is 90 minus Q. Therefore, PHQ will be, these two angles sum up to 180 minus P minus Q. So this angle must be P plus Q, because then only the angles of the triangle will sum up to 180. Now think about it. P plus Q is what? In triangle APQ, P plus Q is clearly 180 minus A. Right? So what we have gotten is angle PHQ is equal to 180 minus A. This is the first fact that we know. We also know that the circle had BC as a diameter, right? So BC is the diameter of the circle. So if I join B to Q, notice here that BQC has to be 90 degrees. Why? Because BC is diameter, then BQC is angle in a semicircle, right? So this is 90 degrees. Great. And now look at the quadrilateral BPHQ. If you look at quadrilateral BPHQ, notice that all 4 points are lies on circle tau. All 4 points are lying on the circle tau, right? So basically this quadrilateral BPHQ is cyclic, right? So we can use the property of cyclic quadrilateral, which will say that the opposite angle should add up to 180 degrees. So we'll use the angle PBQ, plus angle PHQ must add up to 180 degrees, right? This is the property of the cyclic quadrilateral. This angle plus the angle PHQ that we have drawn here must add up to 180 degrees. And let's find PBQ now. Because angle BQC was 90 and this is angle C, we know that this much is 90 minus C. And therefore this angle, the angle PBQ, must be B minus 90 minus C. So that will be B plus C minus 90. And what is B plus C in the overall triangle? B plus C is 180 minus A. So this is 180 minus A minus 90, right? So this is 90 minus A. So what we get is angle PBQ is 90 minus A. And we have already gotten PHQ is 180 minus A. So that the sum of this should be 180. 180 gets cancelled and you get 90 minus 2A is 0. So angle A is 45 degrees. Which is the angle A that we are finding? We have found the overall angle A here. This angle must be 45 degrees in this case. So that is what we were being asked in the problem. They asked us angle BAC, right? So what did we do in this question? We drew the figure correctly. We first figured out the angles due to the orthocenter. We found angle PHQ. We also noted that this BC is a diameter, so angle BQC is 90. And then we spotted that quadrilateral BPHQ is a cyclic quadrilateral. So we can always do opposite angles of cyclic quadrilateral are supplementary. And from there, since we have expressed both the opposite angles in terms of A, one of them is 90 minus A, one of them is 180 minus A. We were able to get the value of A to be 45. So that concludes this problem. In the next video, we'll look at 5 more RMO problems and we'll continue doing content like this and problem solving for Olympiads. till the day of the exam. Hopefully, like you'll have enough practice and this should help you crack the IOQM and RMO exams this year. That's it for this video. I'll see you next time.